So we are inside our GAP software, and yesterday we're looking at how we could do some surface modeling. Open the PowerPoint. Okay, yesterday we look at how we could carry out a surface modeling like this, where we have about 3 wells that are connected to one pipe to the separator. Okay, so we concluded that well A1 and A2 are connected to a single node. Then this is a pipeline. Then we have our well B1 that is connected along the line, then to the separator. We may have a separator pressure of, let's say, 100 psi, and we want to do the modeling of this system to see the amount of mass that will be flowing at each point in time, and also to see the pressure drop along the line, along the piping system. Okay, so if we go to our system, I saved it yesterday. Let me cross-check where I did that. I think it was in a Josephus Sistema internship. All right, so I saved it yesterday. All right, so this is our system that we built yesterday. We have our A1, A2, and A3. All right, so for this A1, we included our Prosper that we built yesterday. If you were not around yesterday, you have to look at the video to see what we did yesterday. We used Prosper to build the well model for A1, A2, and A3, and we imported these models into our system, and we used this model to generate our IPR. Well, what we did not generate was just our VLP. So we have all our wells here, A1, A2, and A3, because we need to know how each well is functioning before we can now know how this well will interact with each other to have a better system performance. So if we start with well A1, we want to input our VLP. So we'll click on this. All right, our Prosper system is already inputted, but we need to define what we want before we can generate our VLP using the Prosper. So once we are at this level, we just go to generate. We go to generate. Once we are at generate, we go to data. All right. So we have these numbers here. These numbers that we have here are just because I try to do the simulation before the class so that we can move faster. Generally, you will not have these numbers here. You have this as empty space. So what we have is our liquid rate. You have to know that our VLP is a very complicated curve to produce. This curve depends on so many parameters. So to generate this curve, they need to know the liquid rate, the manifold pressure, which is our wellhead pressure, In this particular case, since the wells are connected at the wellhead, then we have our gas oil ratio and we have our water cut. So what they are asking now is the set of values of the liquid rates that you need to use. So what we'll do is you come to populate, you give the starting value and you give the ending value, and then you give how many values you want. In this case, we want 20. Once you click on it, we are going to have 20 values that we are going to have between 100 and 8,000. So if I change this to, let's say, 10 to 8,000, if I populate it, we now see there's a difference, but it starts from 10 and then ends at 8,000. Then our manifold pressure now, let's just say it starts from 100 to 500. We could also put it to around 600 to 700. Let's put it around 700, and then let's say 5 values. We populate. We have that. Our gas oil ratio also, and then our water cut. That means we are going to have so many plots, because for each flow rate, let's just take for example that we have a flow rate of 10. It is going to work with a manifold pressure of 100, a gas oil ratio of 200, and all of this water cut. It will now take, for still the same 100, it will take now 300 and work with all of this water cut and generate the various curves and all and so on. Still at 100, we go to 400, work with all of it. Then once you finish with 100, you now go now to 250, and then you repeat the same process. Then when you now finish with 10, you go now to the next liquid rate. You go now to the next liquid rate, then you now repeat the same process. So we have so many plots that we are going to have. So what we are going to do here is we'll say, okay. Then from there now, we generate. We are supposed to generate it for the gap model. So we click here for our gap model, then we generate. All right. So the generation is complete. So we take OK. Then we take OK here. So if you want to see the various plots that have been generated, you come to inspect. Once you come to inspect, you see the result of all of it. So what I may do here is for 10, if I change now, like what I said, we are at a manifold pressure, of 100. If I change this to 250, you realize that the values are changing. If I change it to 400, it changed. If I change it to 500, it changed, and 700, it changed. If I go to the next value of water cut, if I take water cut of 11, as I'm changing every parameter, you realize that the values are also changing. So I may come to plot, and I say plot. All right, so this is a plot of a particular case. Which case? The case that I have highlighted. This case that I've highlighted, that is the plot of that particular case. That's the plot of that particular case. All right, so this is our bill LP that has been generated. All right. So if I want to see all the plots, I will just come to this icon here. Once I click on the icon, I will see all the various plots that are available. So what I will do is I will click on all of them to see all the plots. I will click on all of them to see the various plots that are generated. So we are going to take OK. You see the various plots So we have different possibilities that have been generated. So what the system is going to do now is to pick the best curve that matches our system, that matches well our system based on the water curve, based on the gas oil ratio, based on the manifold pressure and all of that, is going to pick the best curve out of all of it. But we are plotting all of this so that the system is going to match and pick which curve best fits our system. So this is our BLP. You realize that it was originally red. Now what we have here is green. So it shows that that particular curve has been entered. So if I click here, now we may have different scenarios that may occur. So what we want to do now is to choose which scenario to pick so that the system will pick. We may have our VLP that looks like that. We may have our gas oil ratio. We may have our IPR that looks like that. So you realize that our system performance is surely at the point of intersection of the vertical lift performance and the inflow performance relation. But in this case, we have two intersections. So we have to choose which of them is the best value for that system. So if you look at it, you will now see what you have to choose from here. So from here, you can turn off if unstable. It becomes unstable if you have 2 points. If you have 2 points that have an intersection, so it becomes unstable. So if it becomes unstable and you turn it off, it means that there will be no simulation for that system. But we don't want a situation where the system will be turned off. We want a situation where the system can either accept the left value or accept the right value. So here we are going to say allow left-hand side intersection. So we are going to use our left-hand side intersection for this. So if I go back to summary, if I take this as okay, you realize that this world A is no longer circled with the red, which means that all the components that is needed for simulating this system is available for well A. I'll go to well B and I take the same thing, BLP. I go to generate. I take data. I've already inputted the data here. This population, I will start it from 10. I will start this oil rate from 10. I will populate. Our upper limit, I use 8,000 for our upper limit because when we did the simulation in Prosper, we looked at the maximum, what they call the absolute open hole flow, which is the maximum flow rate of our curve after we have produced it in Prosper. We saw that the maximum flow rate was about 8,000. That's why I'm earning at that level. That's why I'm earning at that level. So we'll take okay. Then we'll generate. You can go and verify after that. All right, so it's done. So you can still go to inspect and you looked at all the values. You can go to plot. It has plotted a particular situation that you have highlighted. You can come here and you choose all the various scenarios that we may have in that particular area. And we take okay, and it plots all the various scenarios that we have that the system has to work with to pick the best optimal curve for our simulation. So this is okay. I go now to well B1. Once you go to B1, you realize that A2 is now tick as green. So I'll go to VLP, generate data. All right, this is okay. I'll start this from 10. Start this from 10. All right, that's okay. So I will generate. So the system is now using our Prosper model to do this generation. If you don't input your Prosper model, there's no way. Of course, I did all of this explanation yesterday. If you don't input your Prosper model, There's no way you can generate all of these VLP and the IPR. We are generating them using our Prosper model. So everything is now okay. All right, so all the system now indicates green with no red circle around it. So from there now we can move on. We have defined what we have in our well. We have defined what we have in A2 also and in B2. We now know the type of fluid that is flowing inside the well. We know the pressure condition of the well because of the Prosper model that we inputted yesterday. So what we want to do now is to define how heat is going to be lost in this system. We need to know the rate at which heat will be lost in this particular system. What is the length of this pipe? What is the diameter of this pipe? All of this is going to be used to simulate to get the pressure drop along the system, because our essence is to get the optimal, not maximum, the optimal rate and pressure drop that is required for this system, assuming that we are going to have a separator pressure of 100 psi, because we have a separator pressure of 100 psi. So the system is now simulating to get the best condition under which this various system can operate in order to give us the maximum oil rate that that system can produce. All right, so from there now we need to define also our pipelines. Remember, I said this one, this, and this are not pipeline. These are just links to tell us that the two systems, the two wells are linked to a single manifold or to a single wellhead. But realistically, they can be linked to a single manifold. They cannot be linked to a single wellhead. They can be linked to a single manifold. So what we'll do now here is we'll double click on this. It takes us back to the same system where we had our well A1, A2, but here we are working with this piping system, J3 to J2. That's what we are working with. Now, there are so many things that we have to define here. So the first thing there, we have our environment. We have to look at the environment. What is the surrounding temperature? This piping system, is it buried in a soil? Is it at the surface? If it's at the surface, what is the atmospheric condition? Because the atmospheric condition also will determine the rate at which heat is lost from that system. Because we don't only want to predict the pressure variation, but we want to also predict the temperature variation. So what is our surrounding temperature? So we'll just leave most of this as default, but generally in a realistic case, they have to do all of this analysis to be able to know how heat is going to be lost between the piping system and the surrounding, whether it is buried in the soil, whether they are all buried in the soil, or if they are at the surface, or they are in the marine environment where the environment is made up of water. We have our surrounding temperature. We have overall heat transfer coefficient. What is the oil heat capacity, the gas heat capacity, and the water heat capacity. For the environment now, the next thing there is description. How can we describe the pipe? We are going to describe the position of this pipe with respect to this pipe. So we always use the downstream pipe to define the position of the upstream pipe. Remember, in our oil and gas company, we start from the upstream to the downstream. Downstream is just telling us the direction in which hydrocarbon is flowing. Hydrocarbon starts from the reservoir, moves from the borehole to the flow line to the separator, and they start transporting it either through pipes or through vehicles to the refinery, and from there it moves to the petrol station and to the vehicles and all of that. So we are now, so they describe it as moving from upstream to downstream. That's the direction in which it is flowing. So from that description, this is our upstream and this is our downstream. So we define the position of the upstream based as using the downstream. the nearest downstream position as our reference. So this may be our reference from which all of it is measured. This may be the surface of water. This may be the surface of the earth in a case where the pipes are buried. In a case where the pipes are buried. So this is our reference surface. We have to use the same reference surface for that simulation. We cannot change that. So if we want to describe the position of this particular node, because we are describing the node, the position of the node, that's what we are describing. This is a node and this is another node. If we want to describe that, we will start by first of all describing this downstream position. So in our system, what we have here is 30-inch. That's a 30-inch. That's the description of the upstream. Then we go now. The next is line pipe. So we are describing this pipe now. We are now describing this pipe using this position as our reference. Okay. If we go back to our system, the next thing there is the length of the pipe and the depth of the node. So we look at here, the length of the pipe is 3,000 and the depth of the node is 40-inch. So we come here, we have 3,000 feet, then we have 40-inch. We have 40-inch. What is the inner diameter? The inner diameter, that's the inner diameter there, which is 4. This 4-inch. This one is in feet, and then this one is in inch. So we have 4-inch. We have 4-inch. Look at this. The units are in foot. Then this one, the unit is in inch. We can always change it, toggle it, and change depending on what we have. But we are going to leave it in foot because that's what we have here. This first stroke that you'll see starts for foot, then this stands for inch, which is the diameter. All right. So we have now described this particular piping system. We have described what we have in that piping system. So that's what we have. We have just a single pipe there, so we are describing that pipe. If you have any constraint, you may add a constraint. Maybe you may want to say if the maximum mixture velocity is at this level, the system should stop, or the system should have this lowest minimum or maximum velocity, or inner or maximum line pressure, and all of that. If you have any constraint that you want to do, that you want to add, you may add. If you have any scheduling, that means you may want to say probably along the line, this particular system should start functioning. You may have a situation where you have 2 pipes and maybe you don't want the 2 pipes to start functioning at the same time. You may say, okay, at the beginning, this pipe will function. Maybe after 2 months, this other pipe is going to start functioning. So we are going to give a date for that pipe to start functioning. But in this case, we are going to leave it simple with no constraint. So we leave it there. You now see an arrow there that tells us exactly that we are done with that system. We have defined the rate at which heat is lost in that particular system, since we want to predict temperature drop in that particular system. In this other pipeline, we have not yet done that. We can still come back there and we do the same thing. We'll just leave all of this as default. We are surrounding temperature and all of that. We go to description. We do the same thing. Since we want to describe the position of this particular pipe, this is the depth of this node, but we are using the upstream, the nearest upstream node as our reference. So our reference here will be 50. So if we come to our system here, we first of all start by putting 50. Then the description is a line pipe. I think it's 4,000 feet. It's about 30. Then this is 7, based on what we have. So that's 4,000 feet of length. We have 7-inch of inner diameter. Then this is the depth now of the node. And then we are describing the node based on the nearest upstream node. So our reference point here is the 50. All right, from there, we have done that. So if there's any constraint, we may add, any scheduling, we may add. So we take our system is now okay for simulation. Our system is now okay for simulation. So what we will do is, there are two ways in which you can just run the simulation. We can come here, we see run network solver. You click on it and you run the simulation. You can still come to solve network. I click on it, and the first part I see run network solver. Once I click on it, they will tell me now to define the separator pressure. Our separator pressure in this case is 100. You may want to put some other values to simulate different scenario and see what is the best possible scenario. But in this case, we'll just use our 100. We take next. All right, yeah. So there are different aspects here that you can choose. We may have some optimization. Maybe you want to optimize some parameter and probably get the best possible flow rate. So we may have to take maybe optimize with all constraints. If we have constraints there, optimize with potential constraints only. And then we have rule-based, but in this case, we'll just take no optimization for now. We just take no optimization, then we calculate. If everything is okay, this message box will not show any blue. If it shows any blue, it means that there's a message there that will tell you that there is something that has happened for that system not to complete the simulation. So you have to go to the message, read what you have there, and try to readjust the parameter. Then you come back and recalculate. So we have done the calculation. Go back. All right. So we now see some values that are appearing. There. So we may want to choose which value we want to appear there because we don't know what these values here represent. So I will right click. I'll come to info display. I click on it. I choose exactly what I want to display. So what these values actually represent was the pressure. They actually represented the pressure. That's what this value actually represented. So I may also take oil rate. I click on it. So what I will see now here is the oil rate. It's going to show me the oil rate at the reservoir level, the oil rate at the flow line level, and then the oil rate also at this other flow line level. All right. So if I want to see the results, I may come to these results. I click on it. You may want detailed result by items, by wells, by joints, by pipe, and so on. You may want a summary also. I may come to any of them and I click. I come back to this, our box that we had at the beginning. We had summary, input, and results. So from here now, once I click on the result, it is now giving me the result. In well A1, what we have is our oil rate is 166, our gas rate, our water rate, our liquid rate. There is no revenue here because we did not use any revenue constraint, which would have defined a tax system that is going to use to optimize the revenue, which I explained yesterday. Then we have our mass flow rate, Then we have our hydrocarbon mass flow rate. I may also look at well A1, well B1. I may look also at the various nodes. We have 3 nodes. We have J1 to see the changes in J1, to see the various changes happening in J1. I may look at the piping system also, the piping system from J3 to J2. I look at it to see the flow within that piping system. what is our oil rate. If I look at it well, you realize that this is our oil rate. It's already highlighted in red to tell us that this is exactly what we are looking at. So we have our oil rate, which is 274.75.4. That's the value that we have there. It tells us the amount of water that is flowing in that pipe. What is the mass flow rate? What's the hydrocarbon flow rate? And so on. Then we may also want to know the pressure drop along the various nodes. The pressure drop along the various nodes. So if I come here, once you put your mouse on it, you are seeing the results. You can actually see the results. So once I put my mouse on it, I see the results. I see there's a noise coming from the background. Caleb, you are just disturbing. You're watching a movie and you're not disturbing us. Okay, so what we have done here now is to have a series of wells in a particular area. We see how we can connect these wells together using our GAP software and simulate how the entire system is going to function under appropriate conditions to have what is our best optimal condition, what's the best optimal oil rate, what's our gas rate, and what is the pressure drop across the various points and so on. So that's what we have actually done here to do this. That's what we have actually done here. And you cannot do that without knowing how the entire system is functioning. You need to know how the entire system is functioning. And to know how each of the wells are functioning, we need to build our well model in Prosper, sorry. We need to build our well model for each of them in GAP based on the information that we have for each of them. Remember yesterday, while building the well A1, A2, and A3, we just kept it simple by just changing some parameters. But in real life, that will not be the case. The depth of this well and the depth of this well will not be the same. This one may be a vertical well, this one may be a well that is deviated, and so on. This one may be 10,000 feet, this one may be 7,000 feet, this one may be about 13,000 feet. So the depth of the well will not be the same. So if you have to build a situation like this, you need to have appropriate data for each of the various cases so that you now use your Prosper software to build a simulation to know how the entire system is going to function before you bring it now into your GAP software. Then you extract the IPR from the Prosper file, extract the VLP from the Prosper file, then you now do a simulation to know how the entire system is going to function. But remember, in this our piping system, if I go to input, all right, if I go to input, the first thing there is environment, which I have to include all aspects of heat transfer and all of that. Why did all of this appear? Is because at the beginning, when we're at the method, we choose that the system should do a prediction for pressure and temperature. If you already have a well-balanced situation about the temperature, you might just do only your pressure prediction. You might just do only your pressure prediction. You don't need to predict the temperature. In that situation, you will not need to go and you will not need to determine the environmental heat transfer parameters and all of that. Environmental heat transfer parameter. So in this case, we'll just leave it as what we have done. But it's not a must that you must do that prediction. It's based on exactly what you want to do. All right. So that is just a brief picture of what you can use GAP for. You may not have only 3 words. You may have a situation where you have about 4 or 5 words. You may have a situation where maybe you don't have only a simple word. Let's say for well A1, you have a well that is producing for about 2 or 3 reservoirs. That means we may have to do multi-layer nodal analysis at this level. So it may not just be a simple case like what we have here. It may be some kind of a complicated case where you start from complicated well models to complicated scenarios. to complicated well scenarios, and so on. So you may want to build whatever you want to build using this. We also have another software that can also do a similar situation, that can also handle the same kind of scenario. We call it PipeSyn. We can also use PipeSyn. PipeSyn has two modules there. It has network and it has well module. So we can also use PipeSyn as with the same function as Prosper. Exactly what Prosper is doing, we can use PipeSyn to do that. So we can use PipeSyn to build our well model. Then we go to PipeSyn network, which is in the same software. It's not like there are two different software. So once you open your PipeSyn software, you have your well model and you have your network. So you can still use PipeSyn in order to produce the same kind of scenario. But I prefer to use this because this one had different software that we could use. It had Embal, we have Gap. Okay. Any question? Any question? If there's no question, then I'll upload
Yes,
it.
sir.
Yes.
I have a question. Good evening, sir. My question was back. I don't know if you can put back that gap, but I was asking, for example, on that flow rate, we customize it to show flow rate. Is that flow rate the flow rate of all the three wells? For example, this 6,625. Is it the summation of these three wells giving you this?
Yes, it's a combination of all of these because these two will
Okay.
combine at this node,
Mm,
then flow into
mm,
a single pipeline. So in this our
mm,
piping system, this is our flow rate for a combination of these two wells. Once it gets to this
okay.
node, the flow from this other well B1 now mixed with them, and then it's now moving. So you now have a combination of three wells moving in this particular system.
Okay, so thank you very much. Also, Master, I wanted to ask about this other software that you told us for GAP and that other software, which one is mostly commonly used by experts in the oil field?
They use the two. This one is produced by Petroleum Expert. Prosper is produced by Schlumberger. So most of the time, people will prefer this one because it is easier to use than PipeSyn. But the reality is that from what I've observed, they use the two. It's not like one is most widely used more than the other. So it just depends on the preference of the company. They use the two.
Okay,
That's
thank you.
why when
Also
we
on
were using a software like Wellflow, I told you
mm,
basically that I would not even advise you to be wasting your time with Wellflow that much because it is not even used at all in most company. But this particular petroleum expert is widely used.
okay, sir. When also on this other thing of revenue, for example, if we went to the revenue side, can it show the revenue that we have, or maybe at the separate or different stages?
Yes, the revenue, what I will do now is if I go to option and I take method, I will look at optimization method here. If I have my
Mm,
optimization method here, I will now have to choose revenue to optimize the revenue. Once I click
mm,
on that, all right, I'll take OK. I will come to option.
mm,
I look at edit tax regime. Once I click
mm,
on edit tax regime, I will have my
mm,
tax system. What is the revenue
mm,
from oil? How much is the sale
mm,
of oil per stock tank barrel? What is the revenue from
mm,
the sales of gas also? Because if gas is there, they
mm,
will extract the gas and then they have to sell the gas. But they don't sell water. So water is instead wastage because they have to spend money to process the water. So what is the cost of water processing? If there's any gas lift there, what is the cost of the gas lift, of operating a gas lift? What is the cost of the power there, whether it's electrical power or manpower or whatsoever? What is the cost of the power fluid? Whatever fluid you're using into the power system and all of that. And then what is it? So there are so many costs that you have to put in to define your tax regime. You may have different tax regime for different wells. For example, if I have this case, if I take OK, if I come down to this well A1, when I click on it, if I go to summary, you realize that they are now asking me to give the tax regime. So if I've defined different tax regime, I will now choose which tax regime now will work for well A1. So I have to choose now the tax regime here. Once I choose the tax regime here, if I run the simulation again, it is going to optimize the revenue.
Okay, thank you, sir.
Welcome. All right, if there's no other question, then I think next week we are going to use PVTP. It's still the same software inside Petroleum Expert that is used for equation of state modeling. So we are going to use that next week. I'm going to discuss about the equation of state. Basically, I talked about two types of model. I've been talking about two types of model, the black oil model and the compositional model. So the equation of states is always used to define a compositional model. So on next week, we are going to have a session on that. So what I've done is to give you a brief introduction of the software. I have said this several times. Don't expect that you have someone that will come and teach you every software from start to the end. They give you a brief description about the interface and how it functions. Then you now try to take different scenarios and you start simulating different scenarios to learn better. So don't think that as I'm showing you this software, in 1 year time, I should know the software more than you. I expect that in 1 year time, all of you should be able to know how to manipulate this software more than me. Because most of you are still students. So I expect that in 1 year time, I should be able to call this person and say, okay, maybe I have this particular student wants to work on this software. Can you take the student on this software? So don't just take a software and you just go and sit. That's what is wrong with this generation. People just take things and you just sit on them. And then you just stay at that level. The next thing now is you are going to be asking me tomorrow, sir, you didn't show us how to do this. You didn't show us how to do this. No, I must not show you everything. Use the software, it's at your discretion. Touch it every angle. You can go to YouTube, look at videos, see how you can simulate different scenarios. Once you have known how to interact with the interface, you can do anything with the software. The basic thing is to know how to interact with this interface. Once you have known that, you can do anything with this software. All right, so if there's no question, then we'll meet on Monday.